Good afternoon, everyone. Thank you for coming to the last session of the conference, making it. Thank you so much. My name is Meenakshi Kaushik, and I would like to introduce the co-presenter, Neelima Mukiri. We both work at Cisco. We are part of the Cisco Container Platform team, and we also enable Kubeflow on our platform. And many of our customers are machine learning customers, and they have started looking at distributed training. So what we're going to do is share our learnings as we are helping customers through their journey. So the agenda for today's session is as follows. I'm going to start by describing the use case, which is to compress end-to-end machine learning time. And this is all the way starting from the exploration phase right into the production phase. And then we talk about how Kubeflow makes that very simple. And then finally, we will walk through an example of increasing the performance of your training using distributed training and hyperparameter tuning. And then look at the infrastructure and the OS optimization to make your training faster, and finally provide a summary. So to start by looking at what is the opportunity. So as I mentioned, the opportunity is to compress end-to-end machine learning. So make the pre-processing, training, and serving faster. And there are many ways to achieve that. And I'm going to give an example of 3 ways. So for example, you can reduce the input-output stall so that your data is always available when your training loop needs it. The second is you reduce all your overhead so that you are utilizing your memory efficiently. And then the third is that you distribute your training by scaling up within the node through the GPUs and then scaling out across the nodes and make your machine learning faster. So what we are going to look at is just the last piece of how you can do that, scaling using GPUs. And we are going to look at in the context of Kubeflow. So before we look at what is a Kubeflow, wanted to show a result. So this is the result which we did in our lab. This is on UCS 480ml, which is a Cisco UCS box, which has 8 GPUs. And as you can see that we are doing this TensorFlow benchmarking using the ResNet model. And as we are scaling up the number of GPUs, you can see the number of images per second that we can use in the training has improved. And this we are doing using NVLink. Let's say we were not using the NVLink, a faster link, we would see the same scale up, except maybe the reduction of like 40 to 50%. So this is the opportunity which you have with distributed training. So what is Kubeflow? I know by now you might have listened to it so many times that I'm going to say this once more. It is a collection of tools which makes the end-to-end machine learning lifecycle easier. And the thing is that it is built on top of Kubernetes. So it is as portable as Kubernetes is, which is super portable. So you can actually run it in public cloud. You can run it in a private cloud. It's just a Kubernetes application. And the other thing about the Kubeflow is that the job of Kubeflow is it gives you a very easy interface, and it hides the complexity of orchestrating whatever the tooling which the Kubeflow provides. And it does the underlying orchestration of Kubernetes pod, the secrets, and everything. So it manages for you, and you get this CRD interface. So let's look into the Kubeflow and the tools that the Kubeflow provides. So the first is, and this is where many of our customers are. They have the data, and they are trying to do just exploration. And many of them are maintaining their own notebooks. And so the first thing they like about Kubeflow is it standardizes, and you have a single place where you are not security uncompliant across each of these individual machine learning teams, but you are in the central team, and you're managing the notebook, and you're using the notebook server. So when you're using the notebook server, you can start with a single CPU image, but then within the notebook server itself, you have an opportunity to scale. So let me just give a quick example of that. So if you look here, and I go to a notebook server, so I can start, for example, with if I want to scale from single GPU to a single CPU to a GPU and wanted to scale up, I would choose a GPU image which has all the CUDA driver libraries all installed into that image. And then there is just a simple place where you can add the number of GPUs you can use. So there is a simple command for that. So this is the command. So let me just copy this and show. And then if I just launch this, then now I have one GPU and you can scale it. So within even an exploration phase, you can go from CPUs to GPUs and start scaling up. But what happens underneath is that this notebook eventually brings up just a single pod. So you're scaling up that number of GPUs and that pod, but you're not able to scale out. So if you have to scale out, then you can use, then you go ahead and use the model training operators, which are available within the Kubeflow. So TensorFlow supports variety of model training framework. The Kubeflow supports variety of model training frameworks such as TensorFlow, PyTorch, XGBoost, MPI Job, and it also supports this pre-processing framework, which is Spark. So many of our customers, for example, initially have been just doing data analysis and on using Spark, and they've just started looking at doing some kind of a deep learning. So they are at this phase, and the TensorFlow provides these operators to do just that. And then once you have trained the model, then you want to optimize the model to be as performant as possible, and you can do that using hyperparameter training. And in Kubeflow, there is, and of course, if you wanted to even figure out what model it is, you could use the neural architecture search. And so both of these are part of this tool, which is called Katib, or the library which is called Katib. And then when you're ready to serve it, you could do the serving using KF serving. So I want to thank the KF serving team for getting my KF serving setup up in the hallway yesterday. They have a very cool talk where you can see that KF serving itself is built on a serverless framework, which is Knative. So basically, the serverless framework, when you are sending requests so that it can serve you, you can scale from 0 to as much as you want because you're behind a serverless framework like Knative. And while it is getting served, you can use a single GPU, a CPU, or you can use a GPU. That specification you can do as well. It's called accelerators in KF serving. I encourage you to check out their talk where they describe the exact syntax of doing that. So, so the way the Kubeflow implements, all the tools in the Kubeflow implement their logic is through extending Kubernetes using Kubeflow operators. So basically, it has custom resource definition. And as I mentioned, that it has these different layers, the pre-processing, the training, hyperparameter tuning, and serving. And talked about Spark in the training. So for example, what happens with these operators is, let's take an example of a TensorFlow TF job operator. What it does is that when you're looking at distributed training, in your training code, what you would specify is a cluster spec. And cluster spec is how you want to distribute your training workload. And the TensorFlow job makes it very easy to describe that, as you will see in this YAML file, it makes it very easy to describe your cluster spec. And then underneath, it spins all the pods necessary to maintain that cluster definition. And because part of the TensorFlow job specification, you specify the container image that you want to run, or your training code image that you want to run, it injects the environment variable tfconfig inside that pod so that the cluster spec is now available to your training code. So it reduces, for example, when you're doing distributed training, it is helping you with the distributed training orchestration. So, and similarly, the other models such as hyperparameter tuning, which Neelima is going to talk about, when you want to find the best model, like using a neural architecture search, you are able to do that because it makes it very simple to specify what you want, and underlying it orchestrates all the different pods and other resources for you. So how many of you are familiar with deep neural network? Because I wanted to walk through the layers and wanted to talk about what communication exists between why we need that distributed training communication. So maybe like 50%. So I'll just quickly walk through a deep neural network and just give a high-level view of what communication is needed and how it can be optimized across different layers. So this is a view of a model. And the blue dots represents the different features of the input, and the green dot represents the output. So for example, the blue dots could be the characteristics of a flower. It could be the flower color, the types of the petals of the flower, and the stem of the flower. And the green dot would be what you would, is your output, which describes the species of the flower. So for example, it's hibiscus. The whole idea of finding the model is to find these layers, these hidden layers, which are these orange layers, these layers which, with weights and activation functions, which when multiplied with the input can produce the right output, that it can say that, oh, this is hibiscus. So in this example, the weight is called the model parameters, and the activation function, which is user supplied, is called as a hyperparameter. And what happens is that the input is multiplied by this weight and activation function, depending on the way the arrows are attached to these neurons, and finally you evaluate the weight. So that's a deep neural network. So in distributed training, there are two ways to distribute the training. One is called data parallelism, and the other is called as the model parallelism. So in data parallelism, what happens is that in each of the worker in your distributed training, you add the same model to each of the workers, and you split the data. So your overall data is the sum of the three data, but you have split the data. And then each worker is independently working on its set of data, and then there has to be some communication, and which I'm going to talk about, to make this data parallelism work. So what we have seen so far in TensorFlow is that all the model frameworks support data parallelism. So the model parallelism is where you split the model and have a portion of the model run in one worker and a second portion of the model run in the second worker while you're training on the entire set of the data on that worker. So as you can see here. So although this is not supported in Kubeflow, you can do this manually by pinning each of the subsections of the model to a different device and simulate that model framework, but it's not off the box currently supported. So within the data parallelism, to again dig a little bit deeper as to figure out what communication happens in context of a data parallelism. So let's look at one worker view, and it has this snapshot of data. And what happens is that the way it works is it's a series of forward and backward propagations. So in the forward propagation phase, what happens is that the inputs get multiplied by, as I said, with the weights and the activation function to produce the output. So there is no communication needed across the workers in the forward pass. In the reverse pass or in the backward propagation, what happens is that the output is then compared with the actual output, and the loss function you want to minimize, so you can calculate the gradient. And with that gradient, you try to find the next weight. You find a better weight than the older weight to minimize the loss. So as you can see, when we're finding the weight, we are only finding the weight for this section of the data in this worker. But then the other workers are finding on a different section. So you have to combine or you have to aggregate the weight. So this aggregation of the weight is the communication that happens during the distributed training. So now that we've looked at that, now let's look at how the different layers can impact this. So, so to look at the different layers, we want to start with the first layer, which is the infrastructure layer. So in the infrastructure layer, let's start by assuming that the model is not distributed, so it is running on one GPU in one node. If we want to distribute to a second GPU on the same node, then the bandwidth between the GPUs becomes more important. And so the way the GPUs are connected, that link impacts the performance. And so it can be a PCIe link, or it could be a faster NVLink. So that would impact as you are scaling up within the node. And then if you are scaling from one node, scaling out from one node to the second node, then it's the communication between the nodes, or the links, there's this link speed between the nodes, which becomes important. And then it could be anything like a high-speed Ethernet link, or like, for example, InfiniBand, or any of the other links, and that would impact the performance. So in the next layer, which is the OS layer, This is the layer which exposes the things, functionality into the Kubernetes. So in the OS layer, you would want to expose your, the GPUs, the drivers, right drivers to expose to Kubernetes. And the second thing is it should also be able to expose the NVLink. For example, if you had a faster link to the upper layers. And when the selection is made, so for example, if your workload wants 3 GPUs, it should be able to select the 3 GPUs which are connected with the fastest link rather than with some slow links, because that would impact the performance. And then as we talked, like as I mentioned about Kubeflow, it makes the orchestration of the distributed machine learning framework easier. And so it provides, so for example, I talked about TensorFlow job and the hyperparameter tuning with Katib. It provides a simple interface and then underlying orchestrates pod and other resources for you. And finally, you run, as part of that TensorFlow job or MPI job, you would run your training container. And within the training container, you have a training code. In addition to that, you would have a collective communication layer, which is basically used to communicate. And this is what is communicating your weights. So these weights could consist, these weights which are getting communicated, you can communicate through any number of libraries. For example, there is Nickel, there is gRPC, and each of the model frameworks support many other utilities. So with that, Neelima will continue and walk through the distributed training.
Thank you, Meenakshi. So Meenakshi walked us through the different types of parallelism. So how do the different training pods or jobs communicate with each other? One of the common patterns that we see is using a parameter server. This can be a pod that is separate from the training pods, or it can be a part of the training pod itself. So we'll see an example of both using Kubeflow. So this is an example of specifying a TensorFlow job using an explicit parameter server. So you have, here I have 2 replicas, so there are 2 parameter servers, and there are 4 replicas for the workers, so there are 4 training pods that are running in parallel. The pods can talk to the parameter server that is most closest to them to be optimal in terms of the bandwidth and the communication links. The parameter servers then aggregate the weights within each other and pass the updated weights back to the training pods. If you want to change from this model of asynchronous parameter servers to a synchronous parameter server, it's as simple as removing the parameter server spec in your TF job specification. So it's almost identical to the previous specification that we saw. You just remove the PS section, and I've increased the number of replicas here just to make the picture look nice. So we have 4 replicas. There is no explicit parameter server here, but all the pods are communicating with each other all the time. When would you use one versus the other? So if you have fast communication links between the pods, this model is preferred. More and more this model is preferred because you have all the pods always in sync. They all see the same weights, and there's no drift between them. But if you don't have a fast communication link between the pods, it gets very slow to do this. So you want to use an asynchronous parameter server. We will look at distributed training using an MPI job spec in Kubeflow. The reason being MPI allows you to use multiple frameworks. So this is a TF job specification. TensorFlow with 2.0 allows you to do fast communication across nodes and within a node, but that's only available within TensorFlow. So if you want to use the same functionality with PyTorch or other frameworks, it's easier to use the MPI model. So how does Kubeflow implement the MPI job? This is a very high-level architecture diagram. So you have a custom resource, which is the MPI job. It composes of 2 primary components. One is the launcher, and the second one is the worker. The launcher acts as the orchestrator of the workers. So it creates multiple worker pods and handles all the coordination between them. How does this specification look? So here we have the launcher. I'm saying there's a replica of 1, and I have slots per worker is 1. So there's a little bit of tweaking required here. So if you have the slots per worker specifies how many tasks you want to run in one pod. So I have 1 GPU, so I'm running 1 slot in 1 worker. And the MPI run command here says, in total, I have only two processes, because I'm running only 2 workers, and each of them has a single slot. The worker definition here is very similar. I have 2 replicas, and each of them has 1 GPU, so they have to request 1 GPU from Kubernetes. This is similar to any Kubernetes resource request definition. The only difference being with GPUs, you can't really have a high and a low limit. You just specify what you want, and that's all you get. If you want to scale the MPI jobs, it's just as simple as changing the number of workers that you have and the number of GPUs that you have. So same specification that we saw before, I have updated it to have 3 workers, and each of them have 3 replicas, right? So there's 9 processes that are running in parallel, and all of them are running the TensorFlow benchmark ResNet model, and they are communicating to each other using MPI. So that is why the variable update or the parameter server update mechanism is specified as however. If you want to scale up, that is increase the number of slots in your worker and increase the number of GPUs that are available, you basically update the resources that is specified here. And again, this is the scaling out part where I've increased the number of replicas. So this is an example of an MPI specification. Let us do a quick demo and have this run and hope it works. We just ran it and deleted it, so this is a TensorFlow benchmark that I'm running. It's an MPI job. We'll look at the specification while the pods are starting. Very similar to what we talked about. We have 1 pod, 1 function that is running in 1 worker. You have one launcher, 2 workers, and the workers have 1 GPU that is available. We can look at the launcher pod logs, and it tells you that it is, if you go to the very beginning, you can see that it is starting 2 workers. So here I have worker 1. Is the font visible to everyone? It's too small? I hope. This is better? OK. So yeah, so we have the first pod that is starting here, the second pod here. You will see each of the devices being identified. So we'll have a Tesla V100 that comes up here. So, and then you'll see the actual job running and the training happening. Takes about a minute because I'm just running a sample job, at the end of which it'll accumulate the communication between the worker 0, worker 1, and give you the end result of your model. So going back to the presentation. We'll skip the slides because we already saw that. So that's how you implement distributed training using Kubeflow. We just saw one example of MPI job, but it's very similar irrespective of what operator you choose. TF job is very similar. Any model is very similar, right? So we trained a model, but how do you start? Where did that model come from, right? So you have a user who's looking at their data and saying, OK, this is the sort of architecture that will fit my data, right? So they pick an architecture, train it, and see how well it is performing. It doesn't perform well, they change it, tweak it a little bit, get a next model, and then keep repeating the process until they finally find a model that works for them. And this process is very laborious and manual, so you want to reduce the amount of human effort involved there. And the way Kubeflow allows you to do that is using something called Katib. Katib is a hyperparameter tuner and a neural architecture search. We can argue about whether neural architecture search is also hyperparameter tuning, but it basically does both. It lets you identify the best hyperparameters and the best models for your data. It does that, but it does that in a way using multi-model parallelism. So you have multiple models or a same model with different hyperparameters, and you're training them on multiple devices, multiple nodes using multiple GPUs. So you're distributing each of your model training, but you're also running it in parallel with multiple models. Again, doing this in Kubeflow is very, very simple. So we look at how Katib actually achieves this. There is something called a model manager, which handles this job of creating the models and sending it down to a trial controller. The triangle controller takes each of the models, takes your data, and trains them. It then evaluates how well they're performing and creates the feedback to the suggestion controller, which tells the model manager what type of model or what type of modification it needs to make, or it gives new hyperparameters that you want to try out. This process continues until either Katib finds the model that fits your requirements, or it exhausts the budget that you have specified for it. So this is an example of how you specify a job in Katib. So here we have, you're creating an experiment. So you're saying here that create maximum 12 trials, run at most 3 trials in parallel. So I'm running this on my laptop, and I don't really want to run thousands of trials in parallel, so I have a small spec. And then you say what is your objective. So you want to maximize the validation accuracy here. You can set any objective that you want, any data that's output by your model. And here I'm asking it to identify the best neural architecture. So the algorithm name is neural architecture search. Katib supports a lot of hyperparameter tuning models. So you can do random search, you can do grid search, you can do Bayesian optimization, or if you want to identify the architecture itself, you can use the neural architecture search. The job specification for Katib is very similar to the job specification that we saw for the MPI job. You just say what type of a job it is, either a built-in Kubernetes resource like a pod or a job, or it can be a Kubeflow custom resource like a TF job. And here again, I'm saying this is how you specify a GPU to be used. This is an example of a Kubeflow neural architecture search. So not very clear, but you can see that every suggestion generates the number of layers, the type of activation functions that you want to use, how many neurons are activated in each layer, and runs them through the trials. We didn't want to do that live because it takes quite some time. This is an example of that running, and with the view of the different nodes on which it is distributed. So you can very clearly see that it's run across multiple nodes. So very easy to do distributed hyperparameter tuning using Katib. All right, so we've looked at model training. How do we distribute it? We've looked at hyperparameter tuning. Now, if Katib makes it all so super easy, do we need to do anything else? The answer is yes, right? Often our customers come to us asking us, how do I set up my cluster? Do I go all bare metal? Do I use VMs? Do I use vGPUs? They sound cool. What do I use, right? And the answer is it depends. It depends on what you're trying to do, what kind of resources you have, and how much you want to share. If you have a single dedicated user or team to whom you want to give all your GPU resources, then bare metal may be the best option to go, because you can get the last bit of performance out of your GPUs. There is no interference. There's no sharing, right? But then you're effectively locking down GPUs, which are potentially a very costly resource, right? So if you want to avoid that, and if you have multiple users with whom you want to share, using virtualization is a very easy mechanism. If you combine virtualization with PCI pass-through, you get near native bare metal performance. So there's absolutely no difference in the performance that you see with bare metal or PCI pass-through if you're using GPUs. If you combine that with auto scaling, now you're able to share your GPUs across different clusters. So somebody creates a pod or a workload. They ask for 2 GPUs. The entire workload runs, and the workload is done. So your autoscaler says, OK, I don't need this GPU node anymore. It removes it. And that's now available for another pod to use in another cluster, potentially. What about vGPUs? When do you use vGPUs? If you have diverse types of workloads that you're trying to run, so you're not doing all model training. So maybe some people in your team are doing training. Some people want to do inference. Some people want to just run a Jupyter notebook and do data exploration. All of these have different compute and GPU resource requirements. So in such cases, it's easier to divide and partition the GPU into pieces by using vGPUs or virtual GPUs. So there's a component that goes into your hypervisor layer, which takes a physical GPU and splits it up into fractional GPUs. So you can say I have an inference serving pod. It needs 1/10 of a GPU. And when that pod is done, that 1/10 is freed up, you could, again, combine the entire GPU, give it to someone else. So it's easy to share your resources across a diverse set of tasks if you have different kinds of workloads that are running in your clusters. And let's go a little bit deeper than how you set up your servers. How does the communication actually happen within the server? So this is a topology of the GPUs on one of our servers, C480ML from Cisco. It has 8 GPUs. There are many such servers that are available with 8 GPUs, which you can see, which have similar topology restrictions. So what this gives you is 6 NVLink lanes connectivity between multiple GPUs. It also has multiple PCI switches to connect the GPUs to the CPUs, so you can have fast communication paths. Why does it matter, right? So each of the NVLink lanes gives you 25 gigabits of bandwidth. Together, all of them give you, the 6 of them give you 300 gigabits of bandwidth. If you were to compare it to just a PCIe link, that just gives you 30 GB, it's like a 10x improvement in performance. If we have time, we will do a demo that will actually show how much of a difference it makes. So if you have multiple GPUs that are really connected using fast interconnects, and you're doing things like distributed training, which have a lot of, which are using the synchronous parameter server model, where all the pods are talking to each other all the time, it makes a huge difference what GPUs you pick. Right? If you pick the GPUs that are really tightly connected, you can be really fast. If you pick GPU 0 here and GPU 8 here as the 2 GPUs you give to your pod, then it's basically just the same as running them on 2 different nodes. Right? So you're missing out on the fast connect. So it helps to be cognizant of the resources underneath. As much as Kubeflow tries to abstract it away from us, we also need to have a little bit of awareness. There are improvements going on in the community in the form of the changes to the topology manager, which allow you to do placement, which automatically do placement within a cluster by picking the optimal GPUs. But again, if you're dividing it out across different clusters, then you still need to understand this. I don't think we have time for a demo, so let me conclude quickly. So we saw how Kubeflow lets you take data preprocessing, training, hyperparameter tuning, model serving, any of these tasks in your machine learning workflow, and easily distribute it across multiple nodes, across multiple GPUs, right? How many of you have used something like this, right? So I was thinking of what do I say Kubeflow is, right? I've heard of it referred to as a buffet of different things, right? Because when you come to Kubeflow, it looks like you have everything thrown in. There's just so many operators there. They're doing so many different things. But it's exactly like this. It's like a drill, electric drill. So you have lots of bits there. What it does is gives you a standardized interface, right? So you have Kubeflow, and you take any of these different frameworks, you have the same knobs. You increase the speed on your drill. It doesn't matter what bit you plugged in. It's the same way to do it. It makes it easy for you to switch from one to another, to give a standardized environment to all your consumers of your cluster, and to take advantage of new things that are coming in just as easily. With that, I would like to thank everyone who has contributed to Kubeflow, because without you, we wouldn't be here.
Yeah, exactly.
And huge thanks to the Cisco Kubeflow team that helps us with our customer engagements, answers questions, and helps us anytime we need. And also to the Cisco UCS team who gives us hardware, and again, they're available anytime. They're awesome. Last but not least, thank you so much, all of you. This is last day, last session. I can't imagine how much patience you have to be here, but we really, really appreciate it. Thank you.